Usually when we talk about automation, there is a very specific expectation of immediate, highly visible savings.
Right, like a factory.
Exactly, like a traditional factory assembly line. The math there is incredibly linear. You buy the robotic arm, you plug it in, it starts welding the chassis, and suddenly, you are producing widgets at a fraction of the cost. Welcome to the deep dive, by the way. Our mission for you today is to explore the hidden economics and the actual engineering behind AI coding agents.
It's a great mission because that factory analogy, it's a very comforting economic model. You pay the capital expense for the machine, and you immediately zero out the human labor cost on that specific task. The return on investment is visible, it's trackable, and it fits neatly onto a spreadsheet.
But the moment you step into the world of AI software development, that simple math just completely breaks down. We're looking at a stack of technical notes and developer strategies today, and they show an economic landscape right now that is full of hidden traps and phantom costs. Getting an AI to write your code is getting incredibly cheap on paper, but it might actually be costing your engineering team way, way more than you think.
It is the absolute definition of diagnostic muddy waters. If you are managing an engineering team or, building autonomous agents right now, you are probably feeling this pain point daily.
Absolutely.
You look at the latest generation of models, things like GPT 5.6, and their baseline inference costs are just incredibly low. They've drastically pushed the price-performance frontier. But the fundamental illusion is thinking that a lower sticker price for the model translates to a cheaper verified coding patch.
Right, because if the model itself is cheaper per token, the immediate question is, where is all the engineering budget actually going? I was thinking about this, and the best analogy I can come up with is hiring a wildly inexpensive general contractor to remodel your kitchen.
Okay, I like where this is going.
Right. So you find this contractor, their hourly rate is like $5 an hour, and you feel like an absolute genius.
Until the actual work starts.
Exactly. They start working, but they constantly make mistakes. They install the cabinets upside down. So first, you have to spend your own weekend inspecting their work. Then you realize they burned out the motor on your expensive table saw, so you have to buy them brand new tools.
Which isn't cheap.
Not at all. And then you have to pay them for the additional hours it takes to rip down the drywall and do it all over again. By the time the kitchen is actually finished, that $5 an hour rate has resulted in an astronomical final bill.
That captures the dynamic perfectly, honestly. In the data we're seeing from teams trying to scale these systems, this is known as the total agent cost.
Total agent cost.
Yeah. When developers just look at the API cost of sending a prompt to an AI, they are only looking at the contractor's hourly rate. They are completely ignoring the kitchen remodel reality.
Wait, so if I'm paying a fraction of a cent for the prompt, what is the AI equivalent of breaking my table saw or, ripping down the drywall? Where is the hidden burn rate?
Well, it breaks down into a few highly expensive categories. First, you have context and output. You aren't just paying for the final generated line of code.
Right.
To get an AI agent to fix a bug, you have to pay for the AI to read thousands of lines of existing code base just to understand the state of the system. Then you have tool calls.
Like searching files.
Exactly. Every time the agent searches a file, runs a grep command, or fires up a linter, it's utilizing compute.
Okay, let's unpack this. Because tool calls seem relatively cheap individually. Are you saying it's the sheer volume of them?
It's the volume combined with the biggest hidden cost of all, which is retries. The undiagnosed loop.
The undiagnosed loop?
Yeah, the agent writes bad code, runs the test, realizes the test failed, and tries again. And because models are so cheap per prompt, developers often just let them spin.
Oh, wow. I see where this is going. If the agent fails silently and loops like 40 times, suddenly it's reading the entire code base 40 times in an hour.
And it gets worse. Because while it's spinning in that retry loop, it is triggering your continuous integration pipeline.
Oh, right. CI servers are not free.
Not at all. If your AI pushes broken code that kicks off automated testing suites 20 times an afternoon, you are burning expensive AWS compute time. You also have wall time, which is the actual clock time you, the human developer, are sitting around waiting for the agent to finish its loop so you can move on.
Which brings us to the most expensive factor of all, right? The human review.
Exactly.
If I have to pull a senior staff engineer off their core project to spend 3 hours auditing the AI's spaghetti code just to make sure it didn't introduce a security flaw, I haven't saved any money at all.
You really haven't.
I've actually lost money because I paid the API cost, the CI compute cost, and the senior engineer's salary.
If we connect this to the bigger picture, evaluating an AI coder based purely on its prompt cost, is a fundamentally flawed economic model. If you build your business assuming the token price is your final cost, you will bleed cash until you are bankrupt.
So, if human review and uncontrolled retries are the most expensive parts of that loop, the only logical way to stop the bleeding is to physically prevent the agent from making mistakes that require human eyes in the first place. Like, you have to restrict its environment.
Which brings us to the concept of the harness. The harness is arguably the most vital piece of infrastructure you can build if you want to deploy AI agents at scale.
The harness.
Yeah, it is the scaffolding, the runtime environment that you wrap around the model. It dictates everything.
What kind of things does it control?
It controls the agent's context window, the specific tools it is authorized to invoke, its file-level permissions, and crucially, its stopping behavior.
Let's talk about the context window part of that harness, because I know from the source material that one of the biggest pitfalls development teams run into is something called context dumping.
Yes, context dumping is a massive anti-pattern because models like GPT 5.6 are cheap per token and have massive context windows. Sometimes millions of tokens developers get lazy.
They just throw everything at it.
Right. Instead of using a harness to selectively feed the agent only the relevant files, they just dump the entire repository into the prompt.
Like, here's my entire operating system. Please fix the spelling error on page 3.
Exactly. And the harness's job is to stop that.
Yeah.
Because if you context dump and then the agent hits an error and silently initiates an undiagnosed retry loop, it is reprocessing that massive context dump again and again.
Which just multiplies the cost.
Exponentially. The data clearly shows that context dumping, combined with undiagnosed retries, will instantly erase all the price performance gains you got from upgrading to a cheaper model. A good harness forces the agent to retrieve specific abstract syntax tree nodes or file snippets via semantic search rather than just inhaling the whole repo.
Okay, let's unpack this a bit more. If cost per turn or cost per prompt is a terrible metric because it hides these invisible retry loops and context dumps, what exactly should we be looking at? What is the North Star metric? How should engineering teams actually measure success here?
The metric you have to ruthlessly optimize for is the cost per accepted verified patch.
Cost per accepted verified patch,
Yeah.
not cost per line of code generated. Because, I mean, a generated line of code that breaks the production build is a liability, not an asset.
Exactly. To get an honest, clear-eyed picture of this metric, you need deep telemetry. You essentially need middleware that logs the correlation ID of the initial task, traces every single tool call, records the elapsed wall time, and logs the number of retries.
And I imagine you also have to track the automated checks and the exit codes from the linter.
You do. But most importantly, you have to calculate the time delta between the AI's final pull request and the human engineer actually merging it.
To see how much manual fixing was needed?
You have to quantify the human corrections required to get it over the finish line. If you don't track the exit codes and the human intervention time, you don't know the true cost of that patch.
That makes total sense.
You might look at your dashboard and think a bug fix cost you 12 cents in API tokens. But if it required 45 minutes of a senior engineer's time to untangle the logic, that patch actually cost you $60.
But you can't wrap every single task in the heaviest, most restrictive harness, right? Like, if you force the AI to jump through massive telemetry hoops just to update a version number in a text file, you're killing its utility. You need a way to assign work dynamically based on the risk.
You need a triage system. And the framework that top teams are adopting for this is called the three-rung routing ladder.
The three-rung routing ladder.
It's a way to categorize AI work to prevent these runaway costs before they even start.
Here's where it gets really interesting, though. So rung 1 is your baseline. I imagine this is just bounded discovery and tiny deterministic edits, things like running a reject search to find all instances of a deprecated function, or maybe updating a dependency version.
Exactly.
The AI is on a very short leash. It's cheap, it's fast, and the blast radius, if it fails, is near 0.
That's rung 1. The AI has almost no autonomy. Rung 2 is normal, contained implementation. This is your standard, run-of-the-mill coding task.
Like what, for example?
Say you need to add a new button to the user interface that connects to an existing database endpoint. The boundaries are clear, the outcome is easily testable via unit tests, but it requires actual logic and multi-file editing.
Okay, so the danger really starts at rung 3. When you ask it to implement complex, ambiguous logic, how do you sandbox that without suffocating it? Because rung 3 sounds like refactoring a core payment processing module or migrating a legacy database?
Yes, high stakes.
The requirements are fuzzy, and a mistake could literally take down the entire system.
The real challenge isn't just knowing the rungs exist. It's that the AI agent itself rarely knows which rung it is operating on. AI models are notoriously overconfident.
Oh, they definitely are.
They will happily and confidently hallucinate a solution to a rung 3 database migration while behaving as if it's a rung 1 text edit.
So how does the harness detect a rung 3 failure in real time? Like, how does it know to step in before the agent burns through the budget?
It requires hard escalation triggers. The system needs observable mechanical signals to escalate a problem to a human. It cannot be based on the model's confidence score.
What's an example of a trigger?
For instance, contradictory evidence. The harness monitors the standard error stream. If the AI agent reads a file that dictates a certain variable state, but the test output consistently says the variable is undefined, the harness detects that contradiction and halts the agent.
It's basically parsing the test failure loops.
Yes. Another trigger is repeated verification failure. If the agent runs the tests, fails, pushes a fix, runs the tests, and fails with the exact same error signature twice, circuit breaker trips. Cut it off.
What about irreversibility? If the AI gets confused and decides the best way to fix a bug is to just, I don't know, drop a production database table, how do we catch that before the command actually executes?
The harness uses static analysis on the generated diff before it is ever allowed to execute. It parses the abstract syntax tree. If it detects a drop table command or any command flagged as irreversible, that is an immediate hard escalation.
That's a release.
It also monitors scope. If an agent was assigned a simple bug fix, but suddenly its pull request attempts to touch 50 different files across 5 directories, the harness detects that the blast radius is too broad and stops it.
Right.
And finally, touching any security-sensitive configuration files is an automatic halt.
Okay, so that handles individual tasks. But what if the project is massive? Everything we've talked about so far, the harness, the 3-rung ladder, the escalation triggers, that all works brilliantly for a single issue ticket. Right. But what if I want the AI to build a whole new feature over 3 days? You cannot fit that into one prompt or even one continuous session without the context window degrading into total hallucination.
You really can. And that requires a shift in architecture to what are called stacked agent sessions.
Stacked agent sessions.
Yes, when you have massive multi-stage AI work, you break it down into sequential sessions. But the non-negotiable rule here is that stacked agent sessions must own independently reviewable hypotheses.
So instead of just blindly generating a massive pull request at the end of the week, the session is essentially structured like a surgical residency.
What do you mean?
Well, the AI makes the initial incision, which is creating a specific branch of code. But the attending surgeon, which is the system's invalidation parameters, states explicitly that if blood pressure drops, or in our case, if test coverage drops by more than 2%, the operation stops immediately.
That is a phenomenal analogy. Yes, the AI cannot just hand you a massive block of code and say, I fixed it. It has to define its hypothesis.
Like, I believe the memory leak is here.
Exactly. I believe the memory leak is in the caching layer. To test this, I have created a specific branch. If my load tests pass, the hypothesis is proven. And the strict guardrails for this require explicit base commits. We must know the exact Git hash the AI started from.
So we can trace its steps and roll it back cleanly.
Exactly. The session also requires clear file boundaries. The AI is told, you may only modify files in the caching directory. If you attempt to modify the authentication directory, the session terminates.
Makes sense.
You define the dependencies, and you set specific invalidation conditions up front mechanically, so the session can be safely killed without polluting the main codebase.
So what does this all mean for security? Because as I look at these stack sessions and these guardrails, there is a brilliant paradox in the sources regarding how we treat the intelligence of the model versus the access we actually grant it.
The permission paradox.
Yeah.
It is arguably the most vital security principle when deploying these agents.
Right, because human intuition tells you, like, hey, we just upgraded our backend from a basic model to GPT 5.6. It's so much smarter, its logical reasoning is incredible, therefore I can trust it with the keys to the castle.
It's a natural assumption.
I can let it touch the production servers because it's smart enough not to break them. But the reality is the exact opposite.
Model capability and permission are entirely independent vectors. A model demonstrating stronger reasoning capabilities on a benchmark absolutely does not justify giving it broader authority or elevated access to security-sensitive systems.
But why? Mechanically, why is a smarter model a bigger security risk?
Because of the confused deputy problem, largely driven by prompt injection. Let's say a bad actor drops a highly sophisticated malicious payload into an open-source issue ticket. Your AI agent is instructed to ingest issue tickets and fix them. If you are using a dumb, older model, it might read that malicious payload, get confused, fail to understand the complex instructions, and just throw a syntax error.
It's literally too dumb to be manipulated.
Precisely.
Hmm?
But if you are using a highly capable reasoning engine like GPT 5.6, it is smart enough to understand and follow those complex, malicious instructions. It acts as a confused deputy.
Wow, okay.
And if you have given that smart model elevated permissions, if it has the authority to change passwords or alter database schemas, it will execute that malicious command perfectly. A stronger reasoning engine is vastly more capable of executing a complex, catastrophic mistake if it operates on a flawed premise.
That is terrifying.
You must keep permissions locked down to the principle of least privilege, no matter how high the AI scores on a logic test.
We really have to treat them less like trusted colleagues and more like highly volatile chemical reactions. We contain them in the harness.
That's the only way.
So if I'm a developer listening to this and I want to actually implement this theoretical framework, the telemetry, the routing ladders, the stack sessions, how do I test this in the real world without going bankrupt running endless API experiments?
The methodology for benchmarking this is actually very strict to the sources. If you want to test how well your system manages agent costs, you do not run it on 100 different random tasks. You take exactly one completed, real repository issue.
Just one.
Yes, a bug that your human team has already solved, so you know the exact correct answer in the exact time it took.
So it acts as the control group.
Yes. You run your AI agent on that single issue, comparing different routing paths and harness configurations, but you must run it exactly 3 times for each configuration.
Because AI generation is non-deterministic, the variance means it might get lucky on the first try or hallucinate wildly on the second. 3 times gives you a statistical baseline.
And the critical rule of this testing methodology is that while you test different routes or models, you must keep the harness strictly constant.
Oh, that makes sense.
You cannot change the tools the AI is allowed to use while also changing the prompt instructions. Otherwise, you lose your isolated variables, and you have no idea what caused the success or failure.
It's really just the scientific method applied to LLM operations. What gives me hope is that the industry isn't just sitting around philosophizing about these bottlenecks. We are seeing real infrastructure being built right now to solve this.
What's fascinating here is how quickly the tooling is evolving to meet these specific hidden costs. The ecosystem is shifting rapidly, and we are seeing developers like Alex and Sam, who are explicitly mentioned as pioneers in the sources, building the exact solutions we're talking about.
Let's look at what they're building, because it ties this entire deep dive together. Alex is building something called a retry governor. If you think back to our earlier discussion about the massive burn rate of undiagnosed retries, Alex is building the dedicated automated brake pedal.
It is an infrastructure layer designed specifically to sit between the agent and the API. It monitors the AI's loops, analyzes the standard error streams to understand why it's failing, and forcefully interrupts the agent before it burns through the CI compute budget.
It's the site supervisor for our cheap kitchen contractor. It steps in and says, hey, put the circular saw down. You've tried this cut 3 times and you're ruining the wood. We are escalating this to the homeowner.
Exactly. And on the observability side, you have Sam, who is building a visible routing scorecard. This connects directly back to our 3-rung routing ladder and our need for the cost per patch metric.
Because pulling all that telemetry, manually correlating the API logs with the CI server logs and the GitHub pull request timestamps to calculate human review time, that's a total nightmare.
It's a massive data engineering problem. Sam's scorecard tool acts a middleware that pulls data from all those APIs simultaneously. It takes all that messy, hidden telemetry and turns it into a transparent dashboard.
That sounds incredibly useful.
So an engineering manager can look at a single screen and see exactly which rung of the ladder a specific AI task is operating on, what the context window utilization looks like, and exactly how much that specific patch is costing in real time, including human intervention delta.
Which is the holy grail, total visibility into the muddy waters.
It's a massive paradigm shift. We are moving away from the era of just writing code and entering the era of engineering the complex systems that manage the agents that write the code.
Which honestly gives me a bit of anxiety. And it brings us to a final, lingering question for you to ponder. We started this deep dive looking at the illusion of cheap AI. We discovered the massive hidden costs lurking beneath the surface, the wall time, the CI compute burn, the human review.
Right.
We explored how to physically contain the agent using a strict harness to prevent context dumping.
We examine the mechanical escalation triggers of the three-run routing ladder, the strict invalidation parameters required for stacked agent sessions, and the critical security reality of the permission paradox.
And to manage all of that, we are now building retry governors. We are building visible routing scorecards. We are building AST parsers to act as circuit breakers, and complex middleware to track exit codes and human time deltas.
Which raises a really important question for you to take away from this. As we build increasingly heavy, intricate, and restrictive systems just to keep our AI agents from spinning out of control and burning our budgets, at what point does the infrastructure required to manage the AI coder become more complex and vastly more expensive to maintain than the actual software the AI is trying to write?
Are we building a multi-million-dollar Rube Goldberg machine to manage a $5 an hour contractor? That is the question you have to ask yourself before you deploy your next agent.
Thank you for joining us on this deep dive. Keep questioning the systems being built around you, and we'll see you next time.